And the crazy part is, Facebook processes something like 4 million friend requests every minute. Think about that. 4 million every minute.
Whistles, that's a lot of graph traversal. I mean, that's practically real-time graph analytics on a scale that's hard to even imagine. What happens when that system hiccups?
Oh, it's not pretty. Remember back in 2019 when Facebook had that massive outage? Turns out a big part of it was a cascading failure in their People You May Know engine. The recommendation algorithms went haywire, overloaded the graph database, and brought down huge swaths of the platform. Billions in lost revenue.
Ouch. So beyond just suggesting new connections, these social graphs are actually critical infrastructure now. It's not just a nice-to-have feature, it's keeping the whole thing afloat.
Exactly. It's the backbone of engagement, advertising, and even content distribution. Think about it. If Facebook or LinkedIn stop suggesting relevant connections, people stop expanding their network. Engagement drops, and the whole platform starts to wither. It's existential.
Okay, so we're talking about massive, constantly evolving graphs. How do they even begin to build something like that? What's the basic data structure?
At its heart, it's a graph database, right? Nodes represent people or entities, users, pages, and groups, and edges represent relationships between them, friendships, follows, connections. Think of it like a giant spider web constantly being rewoven.
Simple enough in theory, but what about the practicalities? How do you store and query a graph with billions of nodes and trillions of edges? A relational database would choke, right?
Here's where it gets interesting. They use specialized graph databases like Neo4j, or even build their own custom solutions optimized for social network data. Facebook famously developed its own graph database called Teo, the associations and objects, specifically for this purpose.
Teo. I've heard whispers. So what makes these graph databases so much better than, say, Postgres or MySQL?
It all comes down to how they handle relationships. Relational databases excel at structured data, but graph databases are designed to efficiently traverse relationships between data points. Instead of joining tables, you're directly following edges between nodes. It's orders of magnitude faster for this kind of workload.
Okay, I get the basic graph structure, but how do they actually find the people you may know? It can't be as simple as friends of friends, right? That would return way too many irrelevant results.
Nope, that's where machine learning comes in. It's all about predicting the likelihood of a connection between two people who aren't already connected.
So what kind of features do they use to train these ML models? What signals are they looking for?
Tons. Common friends is an obvious one, of course, but it goes way beyond that. Think about shared interests based on liked pages or groups joined, shared employers or schools, location data, even the similarity of their profile pictures. Everything is fair game.
Skeptical. Profile picture similarity. Really? That seems tenuous.
Hey, every little bit helps. The point is to aggregate as many weak signals as possible to create a strong predictive model. And remember, they're dealing with billions of data points, so even a tiny improvement in accuracy can have a huge impact.
Okay, fair enough. So they have all these features, they train an ML model, but how do they actually serve these recommendations at scale? Do they run the model on every single pair of unconnected users? That sounds computationally impossible.
That's the million-dollar question. They use a technique called candidate generation to narrow down the search space. Instead of considering every single user, they first identify a smaller set of potential connections based on simpler heuristics.
Heuristics like...
Like, say, people who live in the same city and went to the same university, or people who are second-degree connections and have at least 5 mutual friends. These heuristics are designed to be fast and relatively accurate, allowing them to quickly filter out the vast majority of irrelevant users.
So candidate generation is like a first-pass filter. Then they run the more complex ML model only on the candidates that pass the filter.
Exactly. It's a divide-and-conquer strategy. This drastically reduces the computational cost and allows them to serve personalized recommendations to millions of users in real time. Netflix uses a very similar approach for suggesting movies and shows. They don't evaluate every movie for every user. They narrow it down first using simpler rules.
Okay, that makes sense. So we have graph databases, ML models, and candidate generation. What about keeping the graph data fresh? People are constantly making new connections, updating their profiles, joining new groups. The graph is a living, breathing thing.
Spot on. Maintaining data freshness is a huge challenge. They use a combination of techniques, including real-time data streams and batch updates. When someone makes a new connection, that information is immediately propagated to the graph database.
So every friend request triggers a cascade of updates across the graph? That sounds like a potential bottleneck.
It is. That's why they need highly optimized data pipelines and distributed computing frameworks like Hadoop and Spark to handle the massive data volume. They also use techniques like caching and data partitioning to further improve performance. Uber, for example, uses similar real-time data pipelines to track driver locations and predict ETAs. It's the same problem at a different scale.
What happens when someone removes a connection? Does the model immediately forget about that connection, or does it linger in the system?
Good question. That's where things get tricky. They can't just immediately forget about a removed connection because that could lead to instability in the model. Instead, they typically use techniques like decaying signals to gradually reduce the weight of that connection over time.
So the model slowly forgets about the connection instead of abruptly deleting it. That makes sense. It's like how memories fade over time. But wait, doesn't that mean that the model is still influenced by past connections, even if they're no longer active?
Here's where it gets interesting. That's actually a feature, not a bug. By incorporating historical data, the model can learn about patterns and trends that would be invisible if it only looked at current connections.
How so? Giving an example.
Imagine two people who used to work at the same company 5 years ago, but aren't currently connected. If the model only looked at current connections, it would miss that shared work history. But by incorporating historical data, it can recognize that these two people have a higher likelihood of being relevant to each other, even if they're not currently in each other's network.
Okay, that's actually pretty clever. So the model is essentially learning from the history of the social graph, not just its current state.
Exactly. It's like learning from the past to predict the future. It allows them to make more nuanced and accurate recommendations.
What about privacy? All this data collection and analysis sounds like a privacy nightmare waiting to happen.
It's a huge concern, and social media companies are under increasing pressure to protect user privacy. They use techniques like differential privacy and data anonymization to minimize the risk of exposing sensitive information. They also give users more control over their data and allow them to opt out of certain types of data collection. It's an ongoing balancing act between personalization and privacy.
Okay, so what's the practical takeaway for engineers listening to this conversation? What should they do differently after hearing this conversation?
First, think graphs first. When you're designing systems that involve relationships between entities, consider whether a graph database might be a better fit than a relational database. Don't default to tables just because that's what you know.
Okay, think graphs first. What else?
Second, embrace weak signals. Don't dismiss seemingly insignificant data points. Even small correlations can be valuable when aggregated at scale. Think of it like finding the signal in the noise. The more noise you have, the stronger the signal can become.
And finally,
third, optimize for scale from day one. Social graphs grow exponentially, so you need to design your system to handle that growth. That means using distributed computing frameworks, caching, and other techniques to ensure that your system can scale to millions or even billions of users. Plan for the avalanche.
great takeaways. So think graphs first, embrace weak signals, and optimize for scale from day one.
Exactly. And remember, building a social graph is like building a city. It's a complex, constantly evolving ecosystem that requires careful planning and execution.
Well said, Parth. Social graphs, they're not just about connecting people, they're about connecting the dots in the data.